So even though germanium is compatible with silicon, we don't just grow the germanium quantum well directly on silicon. This diagram shows you what happens when you grow one material on top of another. Ideally, you want case B. Case B is the case where the second material is growing in a two-dimensional layer on top of the substrate, and this is ideally what we want. We want the quantum well. However, if you put germanium directly on silicon, you actually get mode C. This is called the Stransky-Krastenov mode. And in some cases, this is an application that you're looking for because you're looking for self-assembled quantum dots. Our quantum dots are not self-assembled. They will be defined as will be described in other parts of this course. So we want growth mode B. And to get growth mode B, we can't grow germanium directly on silicon, but we can grow silicon germanium on silicon. It turns out that in contrast to a material like gallium arsenide, which has to be stoichiometrically balanced in order to make a compound semiconductor, germanium and silicon are completely intermixing. So any composition of germanium inside the silicon leads to a crystalline semiconductor, all the way from pure silicon to pure germanium, any composition in between. This gives us the flexibility to grow silicon germanium on silicon with a low enough germanium composition that actually the growth mode is mode B, the Volmar-Weber growth mode, the Frank-van der Meer growth mode. Volmar-Weber is mode A. So this means that by increasing the germanium content slowly from pure silicon up to some germanium composition, which is not quite pure germanium, but a little bit less, then the germanium can be grown on this silicon germanium, what's known as a virtual substrate. So instead of growing on a silicon substrate, we use this silicon germanium buffer. Now, historically, the simplest way to do this, the most obvious way to do this, as I said, is to start from pure silicon and then reach some final composition of silicon germanium, in this case, about 70%. And this means that the difference between the 70% graded buffer and the pure germanium channel is low enough that then we get this growth mode B for the germanium channel. Now, this silicon germanium layer, as you can see in this TM image, is full of defects. But these defects are necessary because that means that the silicon germanium layer is adopting its natural lattice parameter, which is larger than that of silicon. So that's necessary. These defects are necessary for the relaxation of this material. This grading, however, means that these defects are spread throughout the material instead of all existing at one interface, so that there is room for them to spread out and they can create what in the end turns out to be a high quality layer on the top of this graded buffer. And this graded buffer plus the silicon substrate forms what's called a virtual substrate. From the top, it looks like a substrate of 70% silicon germanium. However, substrates of pure silicon germanium made like that don't exist, are not available. The disadvantages of this process is that to make it work, it needs to be several microns thick, 10, 11, 12 microns thick. And for conventional industrial growth systems like chemical vapor deposition, this is a very long growth time. So sometimes this is available. At research scale, it's usually not done. However, using the plasma-enhanced chemical vapor deposition system that we have available at the laboratory in Como, part of the Politecnico di Milano, we can actually grow this much faster, and the growth modes are in a future section of this talk. In order to alleviate this problem of the long growth time, a strategy adopted by the groups in Ignite that produce this material on a research level adopt something called reverse grading. It turns out that if you do grow pure germanium on silicon, you maybe will not get a high quality quantum well. But if the material is thick enough and all the defects are at the interface, then with a bit of annealing, so some thermal treatment, the germanium on the silicon is actually a pretty good quality. And this works for pure germanium in a way that doesn't work for silicon germanium, because if you do it on the alloy, then you get all kinds of problems happening, but for the pure material, it works. And then from the pure germanium, you go backwards. So instead of starting as we did before from pure silicon up to the germanium content we like, this germanium on top of silicon, we then go backwards to the composition we want. So this is reverse grading. And in this case, it's normal to go from pure germanium down to about 80%. And this whole thing can be relatively thin, about 2 microns, and that means the growth is much shorter, not only because it's thinner, but because historically by CVD, germanium requires a lower temperature and is faster at that low temperature compared to silicon germanium with a high silicon content. So this is faster and shorter to grow by conventional thermal CVD.